Have you ever wondered why we throw salt on an icy road? Or how the antifreeze in your car can possibly keep it from freezing in the winter and overheating in the summer? And what about this one? How do we take salty ocean water and turn it into something we can actually drink? I know, they seem like totally separate puzzles, but believe it or not, they're all connected by the exact same, surprisingly simple principle.
Okay, so let's start with that winter road mystery. You've seen it, right? It's freezing outside. You toss some salt on an icy sidewalk, and poof, the ice just disappears.
How is that even possible?
And then you've got this seeming contradiction with antifreeze. I mean, the name itself says it stops freezing. But that same liquid also stops your car from boiling over in July. How can one substance do two completely opposite jobs? It feels like it shouldn't work.
And finally, this one feels like a modern miracle. Taking a mouthful of ocean water and making it pure and drinkable. It seems like it should be way more complicated, but the secret is actually hiding in plain sight.
So as different as all these problems are, the solution to every single one comes down to a really powerful rule in chemistry. And here's the cool part. The rule doesn't really care what you're adding to a liquid. It just cares that you've added something.
And here's the official name for it: colligative properties. It sounds fancy, but the idea is simple. Certain properties of a liquid change based only on how many little particles you dissolve in it. It doesn't matter what those particles are, sugar, salt, whatever. It's all about quantity over quality. Let me just say that again, because it's the key to everything we're talking about today. When it comes to these properties, chemistry just becomes a numbers game. You're just counting particles. The more particles you dump in, the bigger the effect you're going to see. It's an incredibly simple idea with some really huge consequences.
So how does this just add particles rule actually work? Well, it turns out that adding stuff to a liquid changes it in 4 very specific, very predictable ways. Let's break them down one by one and solve these mysteries.
So it all starts with something called vapor pressure. Just imagine a glass of pure water. The little water molecules at the surface can easily just jump out and escape into the air as vapor. But the moment you dissolve something in it, say salt, those new salt particles get in the way. They're like tiny roadblocks at the surface, making it harder for the water molecules to escape. This means the vapor pressure gets low.
And that directly messes with the boiling point. See, a liquid boils when its vapor pressure gets strong enough to push back against the air pressure of the atmosphere. Since our solution now has a lower vapor pressure to start with, we have to pump in more energy. We have to turn up the heat to a higher temperature to get it to boil. And that's called boiling point elevation.
And you guessed it, the same thing happens in reverse for freezing. For water to turn into ice, its molecules have to line up in this really neat, orderly crystal pattern. But once again, those pesky little solute particles are getting in the way, bumping around and disrupting things. They make it much harder for those ice crystals to form, so you have to get the liquid even colder than usual before it will finally freeze.
And boom, just like that, we've solved our first 2 mysteries. Antifreeze works because adding it to the water in your radiator elevates the boiling point, which keeps it from overheating in the summer, and it depresses the freezing point, which stops it from turning into a block of ice in the winter. And salting the roads works by lowering the freezing point of water to below whatever the air temperature is, forcing the ice to melt.
Okay, so if it's all about the number of particles, you might think a spoonful of sugar has the same effect as a spoonful of salt, but not quite. It turns out some substances give you way more bang for your buck particle-wise.
Let's take regular old table salt, sodium chloride. When you dissolve 1 unit of it in water, it doesn't just stay as one little particle. Oh no, it splits apart. It dissociates into 2 separate ions, a positive sodium ion and a negative chloride ion. So for every one thing you added, you instantly get 2 particles in your solution. You've just doubled your particle count.
Chemists actually have a name for this multiplier effect. It's called the Van't Hoff factor, and we just call it I. So for something like sugar, which doesn't split apart, its I is just 1. But for salt, its ideal I is 2. And remember, our main rule, more particles equals a bigger effect.
And this is exactly why the type of salt used on icy roads really matters. Sugar gives you 1 particle. Standard salt gives you 2. But then you look at something like magnesium chloride. It splits into 3 separate ions, 1 magnesium and 2 chlorides. That means for every 1 unit you put down, you get triple the ice melting power. That's why it's so much more effective when it gets really, really cold.
All right, so we've cracked the antifreeze and road salt puzzles, but this whole idea of counting particles goes way beyond that. It's crucial in biology and in huge industries. And that brings us to our 4th and final colligative property.
And that property is called osmosis. This is all about how water moves across a special kind of barrier, like a cell wall. Water naturally wants to flow from an area where there's a lot of water and not much stuff dissolved in it, to an area where there's less water and a whole lot of stuff dissolved. It's like water is always trying to even things out by diluting the more concentrated stuff.
This process is happening inside every single one of us, right this second. Your cell walls are these barriers. And this is why if you ever get an IV drip in a hospital, that solution has to be isotonic. That just means it has the exact same concentration of particles as your blood, to keep that delicate water balance in your cells perfectly stable. Because here's what happens if that balance is off. If you put a blood cell in a solution that's less concentrated, a hypotonic solution, water will flood into the cell, causing it to swell up and even burst. But if you put it in a more concentrated solution, a hypertonic one, all the water rushes out and the cell shrivels up. Yeah, both are very bad news.
You've actually seen osmosis in your kitchen. When a cucumber sits in a jar of salty brine, water gets pulled out of the cucumber cells and into the brine. That's what turns it into a pickle. And this finally solves our third mystery. In a process called reverse osmosis, we can apply a huge amount of pressure to flip that natural flow. We literally squeeze fresh water molecules out of seawater through a membrane, leaving all the salt behind.
And this whole idea of manipulating boiling points is a huge deal for industry. Now, this isn't technically a colligative property itself, but a very closely related process called fractional distillation also uses boiling points. But in this case, the identity of the molecule does matter. All the different things in crude oil have their own unique boiling points, which lets us separate them out into gasoline, kerosene, and diesel, just by carefully heating the mixture.
So let's just step back and bring this all together. From the salt on our roads to the coolant in our cars, from the cells in our bodies to the water we drink, there is one simple, powerful idea running through it all.
It all comes back to this one beautiful, elegant rule. It's not about what you dissolve, it's just about how many things you dissolve. At the end of the day, a huge chunk of chemistry is really just about counting particles.
It just goes to show you that sometimes the most complex things we see are governed by the simplest rules imaginable. Which kind of makes you wonder, right? If just counting particles can do all of this, what other simple rules are out there, quietly shaping the entire world around us?